So here's a summary of all the stuff that we just discovered about our trig ratios. So the idea, of course, is that we have ourselves a right triangle, and then we're referencing one of the two acute angles. In this case, it's going to be angle A, and the Greek letter that's right there inside of angle A is the Greek letter theta. Theta, alpha, and beta, those are very commonly used for angle measurements in trigonometry. Okay, so in reference to theta, we want to label each one of our sides. We have the side that's adjacent to it, which is AB. We have the side that's opposite angle A, which is BC. And then finally the hypotenuse, the obvious one, the longest one across from the right angle. So in terms of those things, that's how we define sine and cosine and tangent. The sine ratio is the opposite side over the hypotenuse side for every single right triangle. The cosine is the adjacent side over the hypotenuse. And then finally, the tangent is the opposite over the adjacent. Definitely write something down. Draw yourself a little picture and label it. As a matter of fact, whenever you go to solve these problems, that's what you do. You usually have a right triangle that is drawn for you, or you draw your own, and you label which one of the sides is adjacent, the opposite, and the hypotenuse, so you can select one of these three ratios. You never use all three for a given problem. You usually just use the one that's most useful for the given information that you have. All right, now the challenge, of course, is not getting these things all mixed up. So I'm going to give you a couple of different ways to help you remember which one is supposed to be what ratio. Okay, it's pretty easy. There's lots of these little mnemonics laying around. Different math teachers have different ones. So here's one of them. I want you to look at your calculator and locate, I need to pull up a calculator here, and locate your trig buttons on that calculator. No matter what, on every single calculator, I have no idea why they did it this way, but it's very, very useful. They always come in the exact same order. It's first sine, then it's cosine, and then it's tangent. Always on, look at your calculator, look at the one that's on your phone. Now, to get to the one that's on your phone, you'll have to turn your phone in landscape, and that usually puts it in scientific mode, which allows you to find the sine, the cosine, and tangent. Now, a very, very useful thing for you to understand is that your calculators, most calculators are going to default to radians, and you may have to change your settings so that the angle is in degrees for some of these particular problems. Now, this calculator app that I'm using here, though, allows me to, whenever I do the sine, the cosine, and tangent, if I put something in here like 30, I can just hit the little degree button and it puts it into degrees, no matter if it's set to radians or not. Okay, so sine, cosine, and tangent, if you remember that order or just look at the order on the calculator, then here's a mnemonic to help you remember which one is which. It's, oh hell, another hour of algebra. Sine, cosine, then tangent. O over h is opposite over hypotenuse, a over h, adjacent over hypotenuse. Tangent is O over A, opposite over adjacent. Oh hell, another hour of algebra. Okay, that's not the most commonly used. I would say the most commonly used one is the one that is a reference to the totem pole picture at the very beginning of this lesson, and it goes like this. It sounds sort of like a Native American chant. It's SOHCAHTOA. SOHCAHTOA, S-O-A, stands for sine, is the opposite over the hypotenuse. Ka, C-A-H, cosine is the adjacent over the hypotenuse. And finally, toa, T, paired up with O and A, the tangent is the opposite over the adjacent. So pick one of these things to help you remember, or maybe even come up with your own, that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is the opposite side over the adjacent side for any right triangle. All right, let's take a look at an example. Now this example, what we're doing is we're just getting used to the trig ratios so that we can match up the different side lengths and the different angles with those ratios. So it says find the values of the 6 trig ratios for alpha and beta. So alpha is one of the acute angles and beta is the other one. Okay, so let's start with alpha. I'm going to start with alpha, and let's make this one all in green. So directly opposite from the alpha, this is our opposite side here. Okay, and then the other leg that touches or that's adjacent to alpha, which is our 4, that's our adjacent side. And then the one that's across from the right angle, obviously, is our hypotenuse. And we're missing a number for that one. I wonder what it could possibly be. How about a 5? A 3, 4, 5 right triangle. Okay, so what I'm going to do is I am going to find the sine and the cosine and the theta of angle alpha. So remember that anytime I'm doing these trig ratios, they're functions, and the input for that function is always, no matter what, an angle. And specifically, it's one of the two acute angles. You'll see when you get into trigonometry that it doesn't have to be tied to a right triangle. And since it's not having to be tied to a right triangle, the angle we're taking the sine, the cosine, and tangent does not strictly have to be an acute angle. For these right triangle applications, though, they always are. Okay, so the sine is supposed to be what ratio now? Sine is, oh hell, which is opposite over hypotenuse. That is 3/5. Opposite side is our 3. Our hypotenuse side is our 5. The cosine of alpha is equal to, so cosine is another hour. That's adjacent over hypotenuse. That's going to be 4/5. And then finally, the tangent of alpha will be, let's see, oh hell, another hour of algebra. That is opposite over adjacent 3/4. Okay, now let's do the same exact thing except for with beta. Let's see, beta is going to be in purple. So here's our angle, our reference angle now, and that's going to change which one of our sides is opposite, because directly opposite beta is now the 4. This one's now our opposite side. And it also changes our adjacent side because adjacent to angle beta is our 3. Hypotenuse is always going to stay the same. That's convenient. All right, so then let's go with the sine of beta. That's how you write a beta. Anyway, it's like a fish, right? It's a beta fish. It's the opposite over the hypotenuse. Oh, hell. Opposite now is 4/5. The cosine of beta, adjacent over hypotenuse, another hour. That's 3/5. And then finally, the tangent of beta is of algebra, which is opposite over adjacent. It's 4/3. All right, so I want you to take a minute, a second, a nanosecond, whatever. Take a look at these numbers. Maybe you notice some sort of patterns. For example, if we look at the cosine of alpha and the sine of beta, those are exactly the same. If we look at the sine of alpha and the cosine of beta, those two are also exactly the same. Like, why did that happen? Remember what happened was when we did our second set, we had to switch the opposite and the hypotenuse. When I switch the opposite and the hypotenuse, this is always going to happen. Or not hypotenuse, the opposite and the adjacent. When I switch the opposite and the adjacent, then the sine and the cosine are also going to switch too. And what's the relationship between alpha and beta? Alpha plus beta. This is a right triangle. We already have 90 degrees here, so alpha plus beta also has to add up to 90 degrees. They're complementary. And now look what happens when we switch our opposite and our adjacent side for tangent. When we switch our opposite and our adjacent for tangent, we just get a reciprocal. 3/4 becomes 4/3. Something that will always happen. All right, so in the next video, how about video? In the next video, we will extend out another little investigation, kind of give you a little background and a little bit more history about these trig values. Now we're pretty spoiled in that if I wanted the sine or the cosine or the tangent of an angle measurement, let's say 35 degrees, all I'd have to do is put it into a calculator. But what would would people have done a long, long time ago before calculators? That's what we're going to answer in the next video.